Okay folks, so this lesson is about vectors and scalars, and it is the start of P8, so the next topic, which is all about forces in balance. So vectors and scalars are a type of something that we call quantities, and a quantity is simply something we can measure. So I would like you to have a think about what sort of things do we measure? And I'll give you an example. For example, distance is something that we can measure. Distance is a quantity. So take a pause, see if you can write down as many quantities as you can, and then come back and we'll list some. Okay, so we could have distance, we could have velocity, we could have power, we could have acceleration, energy, speed, temperature, time, mass, force, displacement, potential difference. That's a big list of different quantities that you will have already come across in GCSE physics. So these quantities could be split into either vectors or scalars. So a scalar is a quantity that has magnitude. A magnitude, which might be a new keyword to you, magnitude is the kind of scientific way of saying size. So it's where the size of the quantity matters. Whereas a vector is a quantity when size matters, the magnitude, so that has magnitude and direction. So a vector is something where it has a size and the direction matters. So have a think about which of these quantities that you've come across before do you know that the direction that it's acting in matters. Okay, so let's try and do a couple of examples now. So the first example that I want you to think about is distance and displacement. So distance or displacement. You might think that these are the same thing. In everyday language, we might kind of talk about them being the same thing, but they mean different things in physics, and you need to be able to say what the difference is. So let's try and explain this. Let's take the example that if I went to a lake and I decided to go on a walk. So I parked my car here, started here, and I went for a walk around this lake, and then when I got to this bit here, I had lunch. Okay, the distance that I've walked is along this dotted path, but the displacement that I've moved is in this straight line. So the displacement is the distance in a certain direction. So the displacement is distance in a certain direction. So it's a straight line from where you started to where you are currently. What that tells us is if direction matters, then displacement has got to be a vector. Whereas the distance, that's just how many meters I've moved from my start point along the actual path that I've taken. So the direction doesn't matter because I'm just following along this path. So therefore distance is a scalar quantity. Okay. The thing that you need to remember as well is if I continue on with this path round the rest of the lake and end up back where I started, my displacement is 0, because compared to where I started, my ending point is exactly the same, so my displacement is 0. There's no difference between where I started and where I finished. The other example that comes up quite a lot is speed and velocity. Now, you've come across these quantities before, and especially in the kinetic energy equation, you get given it as 1/2 times mass times velocity squared. And in the past, we might have just told you that velocity is like speed, and it is quite a lot like speed, but it's where speed is a scalar quantity, velocity is the vector quantity. So let's just put it into a really clear thing of what we mean by this. With speed, if I've got a trolley that's going in this direction at 10 meters per second, and I've got a trolley that's going in this direction, then I would say that both of them are 10 meters per second. Okay, with velocity, the direction matters, and there's a really simple way that we show this. So if I've got a trolley going in this direction, this, let's call it 10 meters per second, and then if I've got the same in the opposite direction, we would show direction by just making this a negative. So this is minus 10 meters per second. That doesn't mean that it's going less than 0 meters per second, where 0 would be stationary. It just means that its speed is 10 meters per second, but it's going in the opposite direction. Okay, and the place that you've come across vectors more than anything is with forces. So you've done forces in year 7, and let's think about how we would draw a diagram. So let's say, for example, I have a box that's got some forces on it. Okay, so I've got my box here. If I wanted to draw a diagram to show the forces that were on this box, I would probably use arrows to show the force. And what I would do with that as well is I would measure my arrows so that they were as accurate as possible. So I would use a ruler to measure my arrows. So let's say, for example, that there was a 5 Newton force to the right. I would need to come up with a scale. Let's use a marker. So we would have what's called a scale diagram. And this is where you would decide on what 1 centimetre represents. So if I wanted to draw a 5 Newton force going to the right, I would probably want to draw, let's say, a 5 centimetre line. Let's move these pens. So I would draw a 5 centimetre line going to the right. So if that's 5 newtons, then I know that 1 centimetre is 1 newton. And this becomes quite important a bit later on, particularly if you do the higher paper. Towards the end of this topic, we do some scale diagrams. But even if you're doing the foundation paper, when we do about resultant forces in a couple of lessons' time, you need to be able to draw these scale diagrams. Often they'll give you either graph paper in your exam paper, or they might give you kind of centimetre, like square centimetres, and you can do it from that. So it's just about coming up with an easy scale. So either 1 centimetre is 1 newton or 1 centimetre is 10 newtons. It's usually quite a straightforward scale like that. Okay, so this is going to go through the questions from the booklet. So I'll read the question, and then it'll be a good idea for you to have a go at the question and then pause it, have a go, and then come back for the answer. So the first question is, define the terms scalar quantity and vector quantity. So define the terms just means very simply state what does it mean. So a scalar quantity has magnitude but not direction, and a vector quantity has magnitude and direction. Okay, list some common scalars and vectors. So we're just stating in each column which one's which. So I've kept these notes behind here. So if you have a moment now, you could have a go at this question by using these and trying to put them into the two tables. Okay, so we could go across each column and think about, is it a vector or a scalar? So distance is a scalar, velocity is a vector, power is a scalar, temperature is a scalar. Acceleration is a vector. Energy is a scalar. Speed is a scalar. And time is a scalar. Mass, scalar. Force, vector. Displacement, vector. Potential difference, scalar. Okay, some of you might be a bit confused by things like temperature, because you might think, well, we have negative temperatures, which I can see why there is some confusion about that, but you've got to think about, is it negative because of the direction it's going in? So let's say, for example, I've got something that's 10 degrees and I increase its temperature by 5 degrees. Well, I would say that's been 5 degrees change. If I decrease the temperature by 5 degrees, I still say that's 5 degrees change. I don't say that's minus 5 degrees, because minus 5 degrees is kind of on that scale still. Okay, explain whether the following statements are stating vector behaviour or scalar behaviour. So the body had a mass of 45 kilograms. That's a scalar because there is no direction. The weight of the body is due to gravity, so acts downwards. Well, downwards is a direction, so it must be a vector. The speed of the car was constant as it circled the roundabout. So the speed is a scalar, because for speed, the direction doesn't matter. It's worth noting here that if something is travelling in a circle and its speed is constant, its velocity is changing, because if you're travelling in a circle, your direction is always changing. So if it's going in a circle, the direction is constantly changing, so the velocity is changing, even if the speed stays the same. And that just shows us the difference between speed and velocity. So the magnetic field lines act from the North Pole to the South Pole. Well, that tells us a direction. So therefore it must be a vector quantity, because the field lines tell us which direction they're going in. So explain why it is possible for a satellite to have a constant speed but a changing velocity. So this is what I mentioned just over the page. So let's remember that a satellite, if this is the Earth, so let's just draw some stuff on it, and we have a satellite that is orbiting the Earth. Okay, so we've got a satellite that is orbiting the Earth, so it's travelling in a circle. So therefore, the speed is a scalar, and it is basically how many meters are covered per second. Okay, so if it's covering the same number of meters per second, then the speed will be constant. Okay, but as the direction is constantly changing, because it's travelling in a circle, so its direction is constantly changing, then velocity changes as it is a vector. Okay, so explain why drag is a vector quantity. So this is quite simple. Drag is a force. Okay, and forces are vectors because direction matters, and drag is the force that opposes motion. So if I'm pushing this pen here and I'm pushing it to the left of the page, then the drag is going to be in the opposite direction, towards the right. Okay, how would you classify time and electric current? Would they be scalar quantities or vector quantities? Explain your reasoning for each quantity. Okay, so for time is a scalar. So because it does not have direction. We can't go backwards or sideways in time. So for current's a difficult one, and it might have felt like a bit of a trick question, because even though we know that current definitely has a magnitude, and even though we sort of think of it having a direction, because we say about it going from positive to negative, it is actually a scalar. And the reason for that is that even though we think about it having a direction going from positive to negative, it doesn't obey the same kind of rules when we're adding more than one current together. If you're doing the higher paper, we'll look at this a little bit later on towards the end of this topic, because when we add forces together, we have to do it in a particular way, and current doesn't follow the same rules. Okay, so explain how and why an understanding of vectors is useful for airline pilots, sports people, and then engineers and architects. So for airline pilots, we would want to think of things like direction of flight, or wind direction. Those things are important if you are flying an aeroplane, because they're going to impact so they will impact the plane's motion. Okay, for sports people, then you might want to think about the size and direction of a force. If you are, I don't know, kicking a ball, if you're throwing something, or if you're hitting something, any of those things, you're going to think about the size and direction of the force that's being applied. And engineers and architects, they need to know about things like forces, stress and strain, pressure, and the direction they act in. So whether your forces are equal and opposite, and how materials are going to behave. So first I'm going to do the summary, because this is in both booklets, whereas I'll then do the final question for the higher booklet only, the 6 to 8 booklet. So the summary wants us to underline scalars and highlight vectors. So I have my highlighter ready. So Ahmed takes 40 minutes, so 40 minutes is time, which is a scalar, to get ready in the morning. He usually eats around 50 grams of cereal. 50 grams is mass, which is a scalar, with 200 millilitres of milk. So 200 millilitres is a scalar. After breakfast, he walks 10 metres from the kitchen to the bathroom. Well, so here we would probably make the assumption that this is the distance that he moves, because he's not going to move, or he's unlikely to be moving in one direct line. He's probably going to have to move around through a doorway and what have you. So that would be a distance rather than a displacement. Where he brushes his teeth with 2 centimetres cubed of toothpaste. So a volume is a scalar. To get to school, he has to walk 2 kilometres in total. So again, this is going to be a distance rather than a displacement. On the way there, or on the way, he stops off at his friend's house, which is 800 metres east of his house. So this is a direction because it tells us it's east, therefore it's a displacement, which is a vector. After picking up his friend, they walk another 1,830 metres north to get to school. And again, it's given us a direction, so that is a vector. The doors at the school are heavy, and Ahmed has to push against them with a force of at least 100 newtons. So we know that a force is a vector. After school, Ahmed goes for a 5-kilometre jog in the park. So 5 kilometres is distance, which takes him around 40 minutes, and we know that time is a scalar. He aims to burn at least 500 calories a day through exercise, so again there's no direction here, so it's a scalar quantity. After going for his jog, it takes him around 15 minutes to walk back to his house, which is 500 metres southeast of the park. Okay, so if you're doing the 4 to 6 booklet, that's the end of the lesson. If you're on the 6 to 8 booklet, then there's one more question that we can do. So the grid below shows a map with 4 towns on it. The map is to scale. Each square represents 1 kilometre. So for the ease of this, we're going to say each square is 1 centimetre. I think they're actually slightly below, but let's say that they're 1 centimetre for the purpose of this. So a delivery drone must travel from A to D, passing first through town B and then through town C. Draw vector arrows to show the displacement of the drone between each town. So they've got to go from A to D, but they've got to go through B and then through C to get to D. So using a ruler, going to draw from A to B, which is an arrow, from B to C, and then from C to D. Calculate the total distance travelled by the drone. You will need a ruler to measure the length of each vector. So I've got my ruler, I'll measure the length of each of these. So from A to B, is 6.5. From B to C is 3. And then from C to D is also 3. Okay. So if we're calculating the total distance, then we need to add these 3 together. So we'll do 6.5 plus 3 plus 3. It's going to give us 12.5 kilometres. Okay. Another drone travels directly from A to D. Draw a vector arrow to show this displacement. So let me just get a different colour. So we're going to draw directly from A to D. State the size and direction of the displacement from A to D. So get my ruler out again, and we're going to measure from A to D, which is 4 kilometres. So 4 kilometres is the size, and now it's asked us for a direction. So for the direction, you could use a protractor. I can't find mine right now, so let's explain how you could do this. If we know that this is north, okay, so we should know north, east, south, west. The line goes halfway between north and east. So if this is east, it's exactly halfway. Well, we should know that there's 90 degrees between these two. So if it's halfway between those, then it's going to be 45 degrees. So we could say it is 45 degrees from north. You might have done bearings in maths. You might know that this is that a bearing is the angle that it is from north through east. And then how much further did the first drone travel than the second? Well, if we do 12.5 minus 4, then we will have 8.5 kilometres as our answer.